All right, so we're up to 9.2. The assignment is 1 to 16 and then 25 to 32. So I'll lecture for a while and I'll have to make sure I give you enough time to do the quiz afterwards. Okay, so just like usual for quiz days, I'll break you into groups of 3 or 4. You can work on it, but if you want to finish early before our usual ending time of what, 6:55, you may. And it isn't due until next Tuesday's class at 5:40 anyway, so you've got plenty of time to work on it. I don't think it should take you that long. I sort of realized some of you are patterns. Some of you turn it in right away. That's okay. So it's like I finished the class and then within an hour I already get it. Some of you do it at the last minute. You know, that's also okay. A few of you do it like Friday or Saturday or Sunday. That's okay also. But the vast majority are either right at the beginning or right at the end. That seems to be the pattern for you guys. You either give it to me within the first hour or so or the very last hour. But, you know, anything is fine. Okay, so I'll lecture for 9.2 for a while, and then I'll give you the quiz, and then that's that. Okay. So looking at our little mini calendar, we are here. October the 1st. It's already October. Believe it or not. So we're not looking for an exam until quite a ways away. Looks like 27th, Tuesday the 27th. So we have quite a ways until the actual exam. Okay. All right, so we're going to do a concept called continuous functions. So there's actually 2 things going on. Continuous functions, which I think is not that bad a concept, and then something called limits at infinity. Okay. You know, when we have the x arrow and a number, you can go to infinity and you can go to negative infinity also. Okay, just to show you ahead of time what that might look like. The problems at the end, the 25 to 32, not sure you can see it here, but 25 to 32, it says for some of them x, and then there's an arrow, infinity, and some of them is negative infinity. Okay, so x approaches infinity means you plug in bigger and bigger and bigger and bigger numbers, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000. And if x approaches negative infinity, then you're plugging in negative 1,000,000, negative 1,000,000,000, negative 1,000,000,000,000, stuff like that. Okay. But the first set of problems involve continuity. We see words like continuous or discontinuous function. Okay. So if you want to know where we are in the book, 1 through 16 deals with continuous functions. 25 to 32 are the limits involving infinity. That's this stuff here. Okay, and I'll show it to you again. Maybe my book's not the same as yours, but for the benefit of those of you who don't have the book and you're not planning on getting it, this is at least my version of the text. Okay, so look at this. And this. And let's see if I can get the ones at the bottom. That. And then 25 to 32. Here they are. Okay, now there's a very formal definition of a continuous function. Okay, I'm actually not going to go over it much, okay, so you're not really responsible for it. Okay, continuity at a point. Okay, the basic idea of a continuous function is that you can draw it without lifting up your pencil from the paper. So this particular function is continuous everywhere. Right? I can draw the graph. I don't have to lift up my pencil from the paper, and it's continuous. Okay. Now, from a calculus standpoint, these conditions have to hold. I'll just mention it briefly in passing, but you don't really have to worry about this too much. Okay, but I just thought I'd let you know. So continuous at x equals c, let's say. Right. So right at that point there, that dot, the function is continuous. Well, f of c has to exist. There has to be a y value. They're saying the limit has to exist. The two-sided limit has to exist. And furthermore, the two-sided limit is the same as the function value itself. Okay, so in other words, we're not jumping up. We're not putting a hole here. Okay, so this is a formal definition of a continuous function. You don't have to worry about it. You're not responsible for it, but I just thought I'd let you know that that's what it's about. If you were to take a very formal calculus class like Math 110 series or Math 100 series, you might go over this a little bit more. Okay, but for now, we'll just say briefly, if you can draw the graph without lifting up your pencil from the paper, then it's continuous. Okay, and we'll just leave it at that. So continuous discontinuous. So you have to stop, lift up your pen, and then keep going somewhere else. That would be a point where the function is discontinuous or discontinuity, as it were. It's probably best if I just go ahead and show you some examples of that. All right, so we'll jump right in on page 556. And I'll ask somebody right now, do you have a picture that looks something like this in your book?
Yes, everything the same, Professor.
The same?
Yes.
Okay. And do you have these numbers? -5, -5, 1, 3, 0, 2, -4, -2, and 5?
Yes, exactly.
Are those numbers the same, anybody?
Yes. Yes, it is.
They're the same? Okay. So these. All right. So before we look at these numbers, okay, pretend these numbers aren't even there. Let's just look at the graph. Because if you understand what's going on in the graph, you can do these very easily. So pretend you don't see this. You know, that's not much of a pretend that is. Whoops. Camera off here. All right. So this graph goes like this, comes down, and then do you see a hole at -4? Okay, and then it keeps going down, and the dot there, and then it jumps back up here, and it swoops down. Then all of a sudden it comes back up here, and there's a hole, and then it goes smooth up to here. Then there's a dot up here, and then an open circle, and it goes down like that. Then you have to cross this line, and then it goes like so, right? So continuous function, can you draw it without lifting up your pencil from the paper? So clearly for this graph, there are points where you have to jump. So if you follow my tracing along the graph, right? So continuous, 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 not continuous because I have to pick up my pen and keep going over here. Okay, so continuous, continuous, continuous. Oh, not continuous because I have to jump up to continue the graph here. Okay, so discontinuous or not continuous. Okay, continuous, continuous, continuous. Okay, then at x equals 0, I have to jump up again. So discontinuous or not continuous, 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 continuous. Then there's an open circle here again. So in order for me to keep graphing, I have to lift up my pencil, keep going here. Continuous, continuous, continuous. Again, not continuous or discontinuous. I have to jump up and put a dot there. And continuous, continuous, continuous. Lift up your pencil when you cross, what is that? Looks like it's 5. Okay. And then after that, it looks like it's continuous the rest of the time. All right, so that's what's going on for continuous or discontinuous function. If you can graph the function without lifting up your pencil from the paper, it's continuous. Once you jump, once you have to pick up your pen to keep going, then it's discontinuous. All right, with that in mind, it should be pretty easy to knock off all of these. Okay, so it's either continuous or discontinuous. Okay, and you know, we probably don't feel like writing the whole thing. Okay, so how about let's abbreviate C for continuous, D for discontinuous, and you can do that for the homework also. Okay, I mean, I don't think you feel like keep writing CONTINOUOUS and DISCONTINUOUS. Can't even spell it. Okay, so you could just put D and C to make it faster. Okay, so I'll say continuous, discontinuous on your homework and any quiz and any test. You can just put D or C if we know that's what we're talking about. If we know we're talking about continuous or discontinuous, you can just abbreviate C or D. Okay, -5. Okay, here's -5 right here. So does it look like it's continuous or discontinuous? Looks like it's continuous, right? I can draw that without lifting up my pencil from the paper. So 1A is continuous, or you can just put C. Okay, how about x equals 1? X equals 1. Oh, there's an open circle here. So 1B is discontinuous. You can just put a D for me. Discontinuous. I have to lift up my pencil from the paper to keep going, right? Okay, see, x equals 3. X equals 3. Definitely discontinuous, right? So if I'm graphing it, I have to stop, pick up my pen and draw a dot there, and then pick up my pen again just to keep going here. So C is discontinuous or not continuous. Okay, x equals 0. X equals 0, definitely discontinuous also, right? You draw this, then you have to pick up your pen to keep going over here. So D is definitely discontinuous. Okay, and then part 2, A, x equals 2. At x equals 2, continuous. Right? I can draw that part without lifting up my pencil from the paper. So A is continuous. You can just put C. 2B, -4. Where's -4? Here. There's an open circle. So open circle means when I graph right here, I have to lift up my pen to keep going. So 2B is discontinuous, or you can just put a D. Okay, and -2. Where is -2? Right here. Definitely discontinuous. So put a D there. And finally, x equals 5. X equals 5 is also discontinuous because it looks like you graph here, but then you have to pick up your pen to keep going over here. So that's also discontinuous. All right? So it's a pretty easy idea. Can you graph that point without lifting up your pencil from the paper, or do you have to pick up your pen and keep going after lifting up your pen? So that tells the difference between continuous and discontinuous. All right, so that's all about 1 and 2, really. All right, now, for what about these functions? Okay. For most functions that you know of, they're going to be continuous wherever they're defined. Okay, so we have to look to see if there's any undefined values. And if they give you something piecewise like this, okay, if they break it up into pieces, then wherever they break up into pieces, that's a good possibility where the function might be discontinuous. Okay, so I'll show you that right now. Okay, and again, the back of the book has odd answers but not evens. So I'll switch to show you as many evens as possible now. Okay, starting with number 4. Okay, I believe the book matches, my book matches yours for today at least. But we will see. Okay, question number 4 looks like this. Okay, is it continuous at x equals 3? Now, when they give you functions like this, okay, it's always going to be continuous unless you end up dividing by 0. You have an undefined point. Okay, so let's say they told me x equals -3. Right? If I plug in -3, I'll be dividing by 0, so the function is not even defined at -3. So the function is not continuous at -3. How about at 3? Yes, it is. This is continuous everywhere else. Okay, so for number 4, it's continuous. Actually, it's continuous everywhere except at -3. Okay, the point where the function is undefined, -3, it would not be continuous, but everywhere else you can draw it smoothly. That's a property of most of these functions that we have. Okay, now, number 6. Okay, they give you x squared minus 6x plus 8 over x squared plus x minus 20. And they're asking, is it continuous at x equals 4? So just like this one, I'm going to plug in 4 only to the denominator. You don't really care about the numerator. The numerator can come out to be anything. But remember, for fractions, the denominator is not allowed to be 0. So do I get a 0 in the denominator? So over here, I don't get a 0 in the denominator. Do I get a 0 in the denominator here? Well, let's see. I have 4 squared plus 4 minus 20. That's 16 plus 4 minus 20. That is equal to 0. Okay. So the function is not continuous or discontinuous at x equals 4 because I'd be dividing by 0. So if I plug in something and I do not get a 0 in the denominator, it would be continuous. That's a property of these kind of functions. So like number 4, it's automatically continuous because I'm not dividing by 0. Now, for 7 and 8, it's a piecewise defined function. So the only way I can get that is with a graph. Okay. Now, if I look at x squared plus 1, okay, some of you might remember that's a parabola. Okay, it's a parabola that opens up. Parabolas are smooth everywhere. Okay. 2x squared minus 1 is another parabola. Okay. It's smooth everywhere. So the only point in question might be at x equals 1 because that's where it changes what happens. So I'll just plug in stuff. Okay, so for this one, what happens if I plug in 1? If I plug in 1, I'm using the upper rule. So 1 plus 1 is 2. So I have to point 1 comma 2. I plot at some other points like 0, 0, 1. The rest of the graph, I know it's a parabola. It looks something like that. Okay, here x is strictly greater than 1, okay, which means if I plug in 1 here, I'm going to put an open circle. Okay, again, if I have a line underneath it, closed circle, like that one. This will lead me to an open circle. Okay, so if I plug in 1, what do I get? 2 times 1 squared is 2, minus 1 is 1. So open circle. That's really all I need. I know the rest of the graph is a parabola, so it goes something like that. You don't have to graph it very exactly, but that's the essence of it. So there it is. So because it's a piecewise defined function, it's broken into pieces, you might have a point of discontinuity at x equals 1. It turns out you do. Okay? If you look only at that, it's continuous everywhere. If you look only at that, it's continuous everywhere. But because it's piecewise defined, right? We break it up into pieces. The point where you have to break it up into pieces, it might be discontinuous. In fact, it is. Right? So we're going to say this function is not continuous or discontinuous at x equals 1. Okay. And they give us some other functions like 9, 10, 11, and 12. Determine where the function's continuous. For 10, y equals 5x squared minus 2x. Okay. I know this is a parabola. You've probably done some of these in your intermediate algebra class. But if you were to graph them, you don't actually have to. You can make a table if you want to. We don't really care. It's a parabola. It happens to look something like this. And we know parabolas are continuous everywhere. Okay, there's no breaks. There's no gaps. They don't give it to me piecewise like this. I'm not dividing by anything like over here, where you have to watch out about dividing by 0. Okay? So this is going to be continuous everywhere. Parabolas are continuous everywhere. Straight lines are continuous everywhere. Right? Where there might be a question is if you have a fraction, like number 12. Okay, so number 12, 4x squared plus 4x plus 1 over x plus a half. Okay, you don't care about the numerator. The numerator can come out to be anything, even 0. You're allowed to have 0 on top of a fraction. The main thing is you're not allowed to divide by 0. So I just have to check what value for x would make the denominator 0. Okay, so it's x plus a half. What number would make this a 0? You're essentially saying solve the simple equation x plus a half equals 0. And that means x is equal to negative a half. Right? So we're going to say the function is continuous everywhere except at x equals negative a half. Okay, so if I plug in any number besides negative a half, it's well defined. It'll be smooth. It'll be continuous. But only at x equals negative a half, the function's not even defined there. So you would have to lift up your pencil from the paper to keep the graph going. So this function is continuous everywhere except at x equals negative a half. Okay? So that's all you have to do for that one. Now for 14, it's a little bit tricky. It's got a fraction, 2x minus 1 over x squared plus 3. So superficially, at first, you would start off with the same thing and say, well, how do you make the denominator equal to 0, right? So x squared plus 3 equals 0. Let me solve that. Subtract 3 on both sides. X squared equals negative 3. Okay, so stop and think about it. A number squared equals a negative. That can't happen, right? That never happens for real numbers. Okay, so in this class, we usually don't do those imaginary numbers. You might remember doing imaginary numbers, the I stuff, square root of negative 1. And we're not doing any of that in our class. So this can't happen. In other words, the denominator is never allowed to be 0, which means this function is also continuous everywhere. It's a function which is continuous everywhere. Because what number makes the denominator 0? There isn't any. Okay, see, like over here, we would say, what number makes the denominator 0? Negative 3. Right? You can factor this to find 4, and also I think negative 5 will make the denominator 0. Right? What number makes this denominator 0? Negative a half. But this one, even though there's a denominator, it's never going to be 0. So it is indeed continuous everywhere. Okay, and then again for 15 and 16, to give you a piecewise defined function. So again, the place where you might have an issue is at negative 2. Okay, this is a polynomial. That's going to be continuous everywhere. Y equals 2, which is a horizontal line, that's going to be continuous everywhere. So the only thing to think about is what happens at -2. All right, so I come up with a graph of that. So if I can, okay, x cubed plus 10, it's a cubic function. I mean, you could plug in some numbers, but I don't think we have to. We could plug in -2. Let's plug in -2. What is -2 cubed? -2 times -2 times -2. -8. -8 plus 10 is 2. Okay, so it touches here. You can plug in other numbers. You don't really care that much, but it's going to be continuous. It goes like this. Like you can plug in -3. It'd be kind of clumsy. It's not something like -17 or whatever. But anyway, it's curved and it goes like that. Okay. What about y equals 2? Y equals 2. That's a horizontal line. And it goes like this. So this particular graph happens to connect at -2. Right? So if you were only to graph this part, you would have an open circle at front. Okay, so pretend you have an open circle right here. That's how you would graph this, because you're not really including -2. So pretend there's an open circle here, but now it gets closed up if you consider this part. So this function happens to be continuous everywhere, because I know y equals 2, straight line, horizontal line, that's continuous everywhere. This polynomial is continuous everywhere, and they happen to join at the same point, -2, 2. That's unlike this one, where you break it into 2 pieces. They didn't connect, right? Because this was 1, 2, if I plugged in here, but this was 1, 1, if I plugged in here. So they wouldn't connect. So in order for me to keep the graph going, continuous, 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 but right at x equals 1, I got to lift up my pen to keep the graph going over here. So this is not continuous or discontinuous at x equals 1. But when I do the same thing over here, it just so happens when I graph this part, the top, and then when I graph this point, they happen to connect. So this one is continuous everywhere. Right? Okay, so I think I've shown you all the evens up to 16. Okay, and now we'll do the problems at the end. 25 through 32. Okay, so these are limits at infinity, so-called. So remember the limits we did before, right? Well, now we have a limit. I'm not sure if you can see it, but x approaches infinity and x approaches -infinity. Okay, I'm going to talk about 2 and 3 mostly right now. But what is this talking about? Okay, so we have this principle. Okay, when you divide by a very, very large number, you end up with a very small number. All right, so let me write something here. When dividing by a very large number, and that large number can be either positive or negative. We get a very small number, almost 0. Example. Limit as x approaches infinity of 4 over x. Okay, so I divide by bigger and bigger and bigger numbers. I plug in 1,000, a million, a billion, a trillion. This limit is 0. Okay. Think about 4 over a billion. Conceptually, think of it as, 4 over a billion. You have 4 pizzas, and you're feeding 1 billion people. how much does everybody get? Everybody gets 0, right? 1 crumb or something like that, right? I mean, 4 over 1,000 is already pretty small. 4 over a million, even smaller. 4 over a billion, it's really, really small, right? So we say the limit is 0. And the same thing is true if I have a negative infinity. So limit as x approaches negative infinity of, I don't know, 10 over x. Okay. So 10 over negative a million, 10 over negative a billion, 10 over negative a trillion. It's a very small negative number, but it's still like negative 0.00001. We're still going to say that the limit is 0. That's what this is saying right over here. Okay. If you divide by a very, very big number, you get a very small number. Okay. They put p there where p is any power. That means this can be x squared, x cubed, or anything like that. Okay. So let me show you this. Doesn't matter if you have x squared, x cubed. This is still 0. Right? This symbol means you're plugging in bigger and bigger numbers, 1,000, a million, a billion. 25 divided by 1,000 squared, very small. 25 divided by a million squared, even smaller. 25 divided by a billion squared, it's even smaller. It's very, very close to 0. Right? And likewise, if we approach negative infinity, it would be the same thing. Limit x approaches negative infinity of, I don't know, 47 over x cubed. That's still going to be 0. Okay. X approaches negative infinity. That means you plug in negative 100, negative 1,000, negative a million, negative a billion, negative a trillion. What's 47 over negative a trillion cubed? It's like negative 0.00000. It's practically 0 also. Okay, so we have to keep these in mind as we work some of these problems out now. All right, so here we go. All right, so I'll just do the evens, 26 through 32, and I'll let you work on the odds a little later. Okay. So 26, please. Four over x squared minus 2x. All right, superficially at the beginning, you might think it's going to be a big number, but see, if I have a super big number squared, it's big, but 2 times a big number is also big. So what happens when you have a big number minus a big number? You can't really tell, but you can tell if you factor first. Factor out the x. Looks like this. Now I think you can tell that the bottom gets really big. Okay. Suppose I plug in a million. That's what this means. X approaches infinity. 4 divided by a million times 99999. It's a big number. So that's going to be 0. Right? And we're plugging in bigger and bigger numbers. If I plug in a billion, the bottom's even bigger. A billion times a billion minus 2. A trillion. A trillion times a trillion minus 2. A trillion times 999999998. That's super big. So 4 divided by that is practically 0. Okay. Now, 28, 30, and 32, we have to do a little algebra trick for these. So these are a little bit harder. Okay, 3x squared plus 2 over x squared minus 4. X approaches negative infinity. Well, in this case, it actually doesn't matter if you have negative infinity or positive infinity because you're squaring it anyway, right? In other words, I claim if I plug in 100, I get the same thing if I plug in negative 100 because you're squaring it. Right? Or if I plug in 1,000 or negative 1,000, same thing. A million or negative a million, same thing. Okay? So in any event, the whole idea is this is a big number, this is a big number. If you were to take a formal calculus class, this would fall under the category of something called infinity over infinity. This is super big. This is super big. If I plug in negative a billion, this is 3 times a billion squared plus 2, real big, over a billion squared minus 4. That's also super big. That's kind of like infinity over infinity. Okay, so we have to do a little bit of an algebra trick here. Fortunately, these are both second degree, x squared and x squared. Okay, if they're both x squared, then the trick is to do this. You divide the top and bottom by x squared. So what I have in red, so I raised up this 3x squared, kind of put it a little bit higher, raise up the x squared minus 4, and then divide top and bottom by x squared, which is a valid step. Okay. On a deeper scale, you're multiplying the numerator and the denominator by 1 over x squared, so to speak. Anyway, this is a valid step. And then I'll actually do the division. So what is 3x squared divided by x squared? 3. Plus 2 over x squared, there's 2 over x squared. Divided by x squared over x squared, 1. Minus 4 over x squared. Okay, now here's where we use that rule that I showed you earlier. Okay, 2 over x squared. That approaches 0 when x approaches either infinity or negative infinity. It doesn't matter, all right? It's a number divided by a super big number, whether positive or negative. Okay, that arrow means it approaches 0. It's like 0.0000001, right? And this is 1 minus 4 over x squared. Likewise, when I plug in bigger and bigger negative numbers, this is like nothing. It's going to be 1 minus 0.00001. It's practically still 1. All right, so then in the limit, I'll just write 3 plus 0 over 1 minus 0, which is 3 over 1, and so the answer is 3. Okay, so that's the process of finding out a limit like this. You would do the same thing whether it's at infinity or negative infinity. It really doesn't matter. Okay, so these are both x squared. Okay, if they're both x squared, divide top and bottom by x squared. Then actually do the division. That divided by that is 3 plus 2 over x squared. And then in the denominator, x squared over x squared is 1 minus 4 over x squared. And the reason why you write it like that is because now, from what we said earlier, when x becomes a really, 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 really big negative number, this ratio approaches 0. This ratio approaches 0. Then you can just say 3 plus 0 over 1 minus 0. And so the answer is that the limit is 3. Okay. We're done with the problem, but I'll dig a little bit deeper. The idea is that when x is real big, either positive or negative, it's almost like you can ignore the 2 and the negative 4. It's as if to say, just forget about it, and just look at 3x squared over x squared. What's 3x squared over x squared? It's 3. Or another way to think about it is, this person has $3 billion. This person has $1 billion. On this person, okay, you add $2. Say the $2 is insignificant. They still basically have $3 billion. This person, you take away $4. They basically still have $1 billion. So what's the ratio? You would still basically say it's 3 billion divided by 1 billion, which is 3. Right? The plus 2 and the minus 4 are so insignificant once you have such big numbers. Right? It's almost like you can ignore it and just say you got 3x squared divided by x squared, which is 3. Okay.
Professor,
Yes.
in your step 2, 3x squared plus x over x squared, I see that the x squared cancels out, but underneath x squared minus 4 over x squared, it cancels into a 1.
Okay, so
Right?
4 over x squared becomes 0. So the
Yes,
denominator is 1 minus 0.
Yes, but for example, the step above, the 3x squared plus 2 over x squared, you
Yes,
canceled out the x squares.
correct.
But underneath, you didn't cancel out the x squares. You went straight into a 1. 1 minus 4.
Yeah, so I did x squared divided by x squared, which is 1, right? You do x
Okay.
squared divided by x squared, 1, and then you do -4 over x squared. Okay. You basically have 4 divisions. 3x squared divided by x squared, 3, plus 2 over x squared. X squared divided by x squared is 1, and then -4 over x squared.
Okay.
That's it. And now when x approaches negative infinity, this is 3 plus nothing divided by 1 minus nothing, and so the answer is 3.
And what does the zeros mean? You cancel
0 means that's what the numbers approach. Okay. Plug in -1 billion. This fraction is almost 0.
that. Okay.
And likewise, this fraction is almost 0. 4 divided by -1 billion squared is nothing.
Because of the negative infinity.
Correct. Either the negative infinity or the positive infinity.
It'll end up with a 0.
Correct. So this becomes a 0. This becomes a 0. I'll show you some more examples.
Okay. Okay. Thank you.
All right. Okay. You're welcome. All right. Problem 30. Pretty similar vein. Limit as x approaches infinity of 4x squared plus 5x over x squared minus 4x. Let me see, what time is it? I have to make sure you get enough time for the quiz. Okay, I think we're still good. All right, this is second degree. This is second degree. Okay, so same thing. I will divide the top and the bottom by x squared, the degree of the polynomial on top and bottom. They're both second degree. So divide top and bottom by x squared, like this. Now, of course, your question might be, okay, what happens when they're not the same degree? Problem 32 is like that, and I'll show you how to do that. Okay, so 4x squared plus 5x divided by x squared over x squared minus 4x over x squared. The stuff that I haven't read is the new stuff, and since I'm doing the same thing to the top and the bottom, it's a valid step. Okay, so we do the divisions. That divided by that, that divided by that, that divided by that, that divided by that. Okay, what is 4x squared divided by x squared? 4. Okay. What is 5x over x squared? X cancels out, so I have 5 over x. So 4 plus 5 over x. Okay, in the denominator, what's x squared divided by x squared? 1 minus 4x divided by x squared. Well, again, one of the x's cancel out, so I have 4 over x. So now I have 4 plus 5 over x divided by 1 minus 4 over x. And we have the same principle. Okay? If you divide by a super big number, you get a very small number, right? When dividing by a very large number, either positive or negative, we get a very small number, almost 0. Okay? So that's what's happening over here. This approaches 0. This symbol, x approaches infinity, right? It means you plug in bigger and bigger numbers. 5 over 100, 5 over 1,000, 5 over 1,000,000, 5 over 1 billion, 5 over 1 trillion. Those numbers are so small, it's practically 0. Okay? So we say the limit is 0 as I plug in bigger and bigger numbers. Likewise, 4 over x. 4 over 100, 4 over 1,000, 4 over 1,000,000. Those numbers are getting really, really small. They approach 0. So we just have 4 plus nothing over 1 minus nothing, which is 4 over 1, which is 4. So the answer to this one is 4. And again, the idea being also this, in this expression, you really only need to look at that first term, the leading term, and ignore the rest. Okay? In other words, x squared is much bigger than x. Do you agree? I mean, let me pick a billion. Most of us think a billion is a pretty big number, but a billion is actually a very small number compared to a billion squared, right? A billion is a big number, but a billion times a billion is way bigger. In fact, it's a billion times bigger. In fact, the ratio of a billion squared to a billion, that's like saying the difference between a billion and the number 1. Right? The number a billion and the number 1, it's a billion times bigger. In the same logic, a billion squared is a billion times bigger than the puny number, so to speak, a billion. This is way bigger. So in the final analysis, it's almost like you can just cover these up. These are insignificant for super big X. They drop into insignificance. It's essentially 4x squared divided by x squared, which is 4. Now, you can't use that in a quiz or test or the homework, but you can use that just as a mental thought. Okay, I'm expecting my answer to be 4 because these drop into insignificance. So the ratio is essentially 4. But do the work, and you see that you end up with 4. Okay. All right, and then 32, and that's the last one, and then I'll give you the quiz. Okay, limit as x approaches negative infinity, 5x cubed minus 8 divided by 4x squared plus 5x. Okay, this time, the degree of the numerator and the degree of the denominator are different. 5x cubed minus 8, 4x squared plus 5. Okay, so you might say, well, should I divide by x cubed or divide by x squared? Okay, it turns out you can do either. Okay, but let's just consistently divide by the denominator, so x squared. Okay, so divide top and bottom by x squared. You could actually divide by x cubed, but let's consistently say we'll just divide by the degree of the denominator. Okay, so x squared. Right? In fact, you can carry that on to any of these. It's almost like you can say now, okay, forget about the top, I'm going to divide by x squared. Or let's say for this one, had there been x cubed, it doesn't matter what's on top, I'm going to divide by x cubed. Okay, so whatever you see in the denominator, if the denominator is second degree, divide by x squared. If this word x cubed, I'll divide by x cubed regardless of what's on top. Okay? And it'll work. All right, so I'm going to choose to divide top and bottom by x squared. Okay, that's an x cubed there, sorry. All right, so I do the division. What is that divided by that? 5x cubed divided by x squared. 5x. And then what is negative 8 over x squared? Oh, it's just negative 8 over x squared. Leave it alone. Okay, then on the bottom, what is 4x squared divided by x squared? 4. Plus 5x over x squared. You get a cancellation, and you will have 5 over x. Right? All right, and same concept. If you have any number and you divide by a real big number, you end up with a real small number, almost 0. So plug in x approaches negative infinity. Negative a million, negative a billion, negative a trillion. This number on the bottom is so big, this ratio is going to be 0. This ratio is going to be 0. 5 over x. 5 over negative a million. 5 over negative a billion. 5 over negative a trillion. That's practically nothing. So I just have 5x over 4. Okay, so what happens if I plug in a super big negative? Negative 100, negative 1,000, negative a million, negative a billion, negative a trillion. If I multiply it by 5/4, I still get a big negative number. Negative a trillion times 5 over 4, it's a big negative. So the limit is going to be negative infinity. So the answer is negative infinity. Remember, you're plugging in a super big negative. Negative a billion times 5 over 4, it's still a big negative. So the answer is negative infinity. And there we go.
Professor?
Yes, question.
So at the end of there, where it says negative infinity, that's because of the 5x?
It's because of it's primarily because of the x.
Yes, the x.
It's x. It's a super big negative. And then if I multiply it by 5/4, it's still going to be a big negative. Right? So the answer
And
is
then where it
negative
says over 4, that's over 4, not over .4, not over 0.4.
That's a 4. That's not a point there. That's a smudge.
Okay, thank you.
Although that wouldn't change anything anyway.
Right, okay, thank you.
All right. Okay, folks, I'm done. I know some of you had chat questions, so let me check the chat for what some of you had. Okay, so Jonathan, okay, got you. Arturo, please send me an email. Okay. My speaker has a bit, yeah, I know sometimes my voice vibrates, and I noticed that in the video later. It kind of go, or whatever. I can't really control that. I'm not intentionally trying to go, but it just comes out, but whatever. That's just the way it is. Okay, and yeah, that's it. Okay, so quiz time. So I'm still recording also. So everybody get a piece of paper and get your cell phone cameras on, because I need you to take a picture of this, but it is still going to be recorded. And then I'll break you up into your groups, and then you work on it from now until what, 6:55. But if you want to end early, you may end early, and it's not due until our next class meeting, which is a Tuesday, right? Okay, so get your cell phones out, please. And here we go. Okay, I think I'm gonna have to break this up into parts. Okay, so sorry, maybe 2 pictures. Question 1 and question 2. Okay, so question 1, you've got a squiggle graph here, open circle, closed circle, open circle. Okay, these are meant to be 1. Okay, so find the limit as x approaches 0 coming from the left. The limit as x approaches 0 coming from the right. No symbol means 2-sided limit. And then f of 0. Okay, so you should know what that means, hopefully. Okay, so one more time. The graph comes like that, like so. Dot, open circle, goes like that. Find the limit as x approaches 0 from the left. Limit as x approaches 0 from the right. Limit as x approaches 0, so 2-sided, and f of 0. Okay, second picture, maybe. Find the limit by using algebra. Okay, don't plug in 0.99 or 1.001. Do the algebra for that. Limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, one more time, or if you want to write it, you may. Limit as x approaches 1, x squared minus 1 over x minus 1. Okay, I believe that's enough time. Okay, so go ahead and get started. I'm going to turn this off. I'll set up the Zoom rooms in a second, so bear with me. Go ahead and get started, but I'll put you in your rooms. And then once you're in your rooms, you can talk about it, but you can leave anytime between now and 6:55, and you have until the next class meeting Tuesday at 5:40 to turn it in. Okay? All right, I think I've given you enough time, but this is still being recorded, so if you never got it, you can ask your classmates or the people in your Zoom room, and worst case scenario, you can find it on the video. Okay? So let me stop the share. And